Hello, so in this video we will talk about linear recurrence relations. Typically we will talk about recurrence relations of order 2. So if we want to have a recurrence relation, this can be given by an, this is equal to some constant times an minus 1 plus another constant c2 an minus 2. Now this is linear because it has um, all the a n minus 1 a n minus 2 have degree maximum 1, and it is homogeneous because each term has uh, an in it. So for example, if I want to clarify it, if I had a relationship which has a2 is equal to a1 plus 1, this is not homogeneous because this term does not have any a in it. Okay, now what our job is to find the solution of this. Okay, so in order to find the solution of this, first of all we have to introduce a characteristic equation. So the characteristic equation goes like this. We have r squared minus c1r minus c2, this is equal to 0. This is known as characteristic equation, and the roots of this equation are characteristics roots, but let's say they are denoted by r1 and r2. Okay, we will see there is some condition on r1 and r2 later. Okay, so what our conjecture is that an is equal to alpha 1 r1n plus alpha 2 r2n. So now this is actually a sequence, so we should put it like this, or we can put it in separate form like this. It's up to you. So this sequence is a possible solution of the recurrence relation. Okay, now we have to prove it. Okay, we have to prove that if we have a recurrence relation of this form, then the solution is of this form, and then we have to prove that if we have a solution of this equation, then solution has to take this kind of form. Okay, so first of all let's do the first forward part. So what do we have? We have an, this is equal to c1 an minus 1 plus c2 an minus 2. So what is an minus 1? An minus 1 is alpha 1 r1 n minus 1 plus alpha 2 r2 n minus 1. And what is an minus 2? Let's just say c2 first. We say alpha 1 r1 n minus 2 plus alpha 2 r2 n minus 2. Okay, now can we use some algebra here? Of course we can. We can take alpha 1 r1 n minus 2 common, and we can use c1 r1 plus c2, and then I can say plus alpha 2 r2 n minus 2 times c1 or 2 plus c2. Okay, now what is this guy? Remember, our r1 and r2 are solutions of this equation. Okay, so then if this means that r1 squared minus C1 R1 minus C2 is equal to 0, which means that R1 squared, this is equal to C1 R1 plus C2. So this means that I can plug R1 squared here, and similarly by the same token I can plug R2 squared here. So my AN will be A1 R1 N plus alpha 1 R1 N and alpha 2 R2 N. So this is what we want to prove. Okay, so we started with some some AN minus 1 and AN minus 2, and we came up with the same form for AN. This is kind of a mathematical induction kind of a forward proof. But now let's go backward. Okay, now let's say that we have initial conditions. So now we have initial condition is um, A0, this is equal to some constant C0, and A1, this is equal to some constant C1. Okay, now this is uppercase C0 and C1. This has nothing to do with these coefficients. So if we do that, then what we do, and our uh, form is how. So we have AN, this is equal to alpha 1, I'll just write it again, plus alpha 2 R2N, which means A0, this is equal to alpha 1 plus alpha 2, which is equal to C0, and sorry, A1, this is equal to this is equal to what? Alpha 1 R1 plus alpha 2 R2, which is equal to C1. Now solving these two simultaneously, we will get alpha 1, this is equal to A1, not A1, A1 is also right. You can write C1 minus R2 C0 divided by R1 minus R2 and alpha 2, this is equal to C0 R1 minus C1 divided by R1 minus R2. Okay, now we have alpha 1 and alpha 2. So what we want to say is, these alpha 1 and alpha 2 are such that they conform with the initial conditions. So now we say, so AN is a solution and alpha 1 R1 N plus alpha 2 R2 N is also a solution. But we should have a unique solution, right? We should have a unique solution to this recurrence relation. So this means that this in fact is a solution. Okay, so just a recap. First, what we assume that AN is a solution, and we check whether this recurrence relationship was satisfied or not. Then for the backward case, we assume some initial conditions and found the value of alpha 1 and alpha 2 for those initial conditions. And since some AN was already a solution, we assume that. And for alpha 1 R1 N plus alpha 2 R2 N will be a solution for these values of alpha. And this means that AN is equal to this alpha 1 times R1 N and this alpha 2 times R1 R2 N. Okay. So this whole story can be used. So application can be to find. Let's see. We want to find an explicit formula for the Fibonacci sequence. Let's do that. Let's apply this whole story to find an explicit formula for the Fibonacci sequence. So let's apply what we just learned to a very famous Fibonacci sequence. So the Fibonacci sequence, just as a recap, goes like this. It starts with 0, and then first two are 0 and 1. Then every number is the sum of the previous two. So 1, 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, and 13. 8 plus 13 is 21, 34, and so on. Now, this relation is, understandably, it is given by an. This is equal to an minus 1 plus an minus 2. So every number in the sequence is the sum of the previous two numbers. Okay, so what is our c0 c1 here? This is 1. What is our c2 here? This is also 1. So our characteristic equation will be r squared minus r minus 1 is equal to 0. If you use the quadratic formula and find the roots of this equation, you will get r1, this is equal to 1 plus root 5 over 2, and r2, this is equal to 1 minus root 5 over 2. So let's recap. What is our initial conditions? C0 is 0 and C1 is 1. And we have alpha 1, this was equal to C1 minus R2 C0 over R2 minus R1, and alpha 2 was equal to C0 R1 minus C1 divided by R1 minus R2. Okay, so let's plug in all the values. Our C1 is 1 and our C0 is 0. Okay, and R2 minus R1, from here we can say R1 minus R2, this is equal to root 5. So I get root 5 here. Similarly, alpha 2, this is equal to 0 minus 1 over root 5, which is equal to minus 1 over root 5. So our final equation should be alpha 1. Alpha 1 is 1 over root 5. R1 to the n. R1 is 1 plus root 5 over 2 to the n. Then alpha 2, negative 1 over 5. And 1 plus root 5, 1 minus root 5 over 2 to the n. Okay. So I find it pretty amazing that a sequence which is actually every number is a sum of the previous two numbers, this can be written as a closed form expression here. Okay, so as a recap, we had um, we presented a method to solve linear recursive relationships which are typically homogeneous, and we we use a characteristic equation to find the roots. Okay, now note that this method will not work if r1 minus r2 is equal to 0. Okay, because remember we have alpha is given in terms of this guy. So if this guy denominator is 0, then we cannot find alpha. So this is something to keep in mind, that this only works when r1 minus r2 is equal to 0, and this characteristic equation has no roots with multiplicity. Okay, so but most of the, as a simple case, this will work. Okay, so this was the purpose of presenting this method. Okay, so thanks for watching. Hope you liked the video.